In this video, I'm going to explain and demonstrate idea of a limit. Okay, so what you see in front of you, okay, I have a definition which I'll explain just a minute. Okay, I have this kind of thing which you probably might not be familiar with. Okay, and that's an example of a limit. Okay, here's my definition. Okay, and this is not a definition you read in a book or see online, but it's my idea, my idea, the best way I know of expressing to people that are looking or watching this what a limit is. And so I say a limit is a y value. A limit is definitely a y value, like same as when you plug a x value into a function and you get a y answer, y value. And that's what a limit is. It is definitely a y value. It's something that we'd anticipate that we connect with the y-axis. Limit is a y value that is the anticipated result of calculating y values from x values that get closer and closer to a particular x value. So hopefully when I do some examples that will be clear as we go. So that's my idea of what a limit is. So let's go up to what I had. Let's see, I had this highlighted a minute ago. All right, the LIM, as you can imagine, that's just an abbreviation for the word limit. Okay, our function is x squared. Okay, so that's our function. That's what we're going to be substituting into, x squared. Okay, and now this down here at the bottom, probably not familiar with. Okay, I got a little x, I got a little arrow, and I got a little 2. That is pronounced as x approaches. That little arrow is really standing for the word approaches. And it's approaching the number 2. So a limit is actually a device that we plug in x values that get closer, that get really close to 2, but not actually substitute into. But I'm going to contradict what I just got done saying just right now and say we will be able to plug in some cases the actual number that we have there. We will plug in 2. Okay, but I don't want to get ahead of ourselves. I'll try to explain that. It's kind of a complex, a concept developed, very powerful concept developed by Newton and maybe Descartes, pronounce his name right, and very powerful concept that we use for calculus. So let's go ahead and do an example. Okay, there's my definition. I'm going to start with the function y equals x squared. Okay, so I have my chart. I have actually graph this. There it is in purple. And so that's the function f of x equals x squared. Okay, I want to find the limit of x squared, that function, as x approaches 2. So what I do is I'm going to pick values for x, and I'll get corresponding output values, y values. Alright, well I'm going to pick x to be 0, and of course when we put 0 into this function, y equals x squared, we get 0 squared, which is 0. So let's graph this down here on the graph. Okay, so 0, 0. Alright, there's our point 0, 0. Alright, next point I'm going to substitute is a positive 1. Okay, when I put 1 into that function x squared, I square 1, I get 1. Okay, graph that, I have 1, 1. Okay, now I'm trying to get to the number 2. It's approaching the number 2. Okay, so in some cases at least I cannot actually substitute into. So let's just for the right now say I can't substitute 2. So here's x equals 2 down there on the x-axis. Alright, so I'm going to pick, instead of plugging in 2, I'm going to substitute 1 and 1/2. I'm going to get closer to 2. Okay, alright, 1 and 1/2, that's the same as 3 halves. And when I square the 3 and the 2, I get 9/4. And that's 2 1/4. Okay, so when I substitute 1 1/2, I get about 2 1/4. So that smaller dot right about there. It's closer. Alright, so I'm going to get a little bit closer, but not actually use 2. I'm going to use 1 3/4. Okay, that's close to 2. Okay, and that is the same as 7/4. And when I square the 7 and the 4, I get 49 over 16. And 16 goes into 49 3 times and has a remainder of 1. Okay, so when I use 1 3/4, I get just over 3, just barely above 3. So that would be that point right there. Okay, and I'll do one more point from below. Okay, so I'll use 1 7/8. Alright, that is equal to 15 over 8. When I square both the 15 and 8, I get 225 over 64. 64 will go into 225 3 times. 64 times 3 is 192, and 225 minus 192 is 33. So it's really the same as 3 and 33 over 64. Really, really, really super close to 3.5. Just a tiny bit over 3.5. Okay? Alright, so when I get closer to x, like 1 7/8, really, really close to 2 on the x-axis, I'm getting up here. Okay, so about 3.5, right about there. Alright, so keep our attention on these values over here, the y values. Remember, limit is a y value. Okay, we had a 0, then a 1, then a 2 and a 4, then a 3 and 1/16, 3 and 3/64. Now I'm going to pop over the 2. Okay, now I'm going to use 2 and 1/8. Okay, and I'll use 2 and 1/4, and I'll use 2 and 1/2, and I'll use 3, and I'll use 4. Let me start with the bottom at 4. Okay, I'll plug 4 into the function y equals x squared. 4 squared is 16. Okay, so when my x value is 4, way down here, way over here to the right, that's 4. My y value is way up here is 16. Okay, way up here. Okay, alright, so I'm going to plug in 3 this time. Okay, 3 squared is 9. Okay, so 3 on my x-axis, my y value is a 9. It's right there. Alright, so 2.5. That's the same as 5 over 2. When I square the 5 and the 2, I get a 25 over 4. 4 goes into 25 6 times and has a remainder 1, 6 and 1/4. So at 2.5 on the x-axis, I get an answer of 6 and 1/4. So that would be, that's a 2.5, about 6 and 1/4, right about there. Alright, and 2 and 1/4. That is 9 over 4. Square both of those, you get 81 over 16. 16 goes into 81 5 times, got a remainder of 1. So at 2 and 1/4 on the x-axis, I get an answer of 5 and 1/16, just barely above 5, right there. And we'll do 2 and 1/8. Okay, 2 and 1/8 is same as 17 over 8. When I square 17, I get 289. Square 80 gets 64. 64 goes into 289 4 times, because 64 times 4 is 256, which is smaller than 289. Then 289 minus 256 is 33. Okay, so 4 is 33 over 64. Alright, so the key we want to look out is here. We're approaching 2. Okay? We're approaching 2. Alright, so I pick numbers that get closer and closer to without getting to be 2. So I pick 0, then I pick 1, then I pick 1 1/2, then 1 3/4, then 1 7/8. But what are the outcomes? What are the answers? I get it because that's what my limit's going to look like. My answer is not 0. Okay, my answer is not 1. My answer is not 2 and 1/4. It's not 3 and 1/16. So it's bigger than 3 and 1/16. These numbers keep going up. 3 and 33 over 64, the roots is really, really close to 3.5. Okay, so it looks like it's a little bit bigger than 3. And then when I pick numbers that are bigger than 2, like 2 and 1/8, I get numbers that are 4. So from basically these values right here, we can kind of anticipate what our limit would be. Okay, all right, so 3 and 33/64 and 4 and 33/64. If we kind of look at those trends, we think the limit might be 4. Okay, and it actually is 4. It actually is 4. Okay, and I'll show you at the end why it really is 4. Let's try another example. Okay, all right, this time I have f of x is square root of x. Okay, all right, which is the inverse function of x squared. So this graph looks a lot different. It starts at 0, y equals 0, goes up. Okay, so here's my question. Okay, what's the limit of this square root function? Okay, as x approaches 4. Okay, so we need to find values that are close to 4. So let's see, I'm going to pick an x and y. Okay, so I'm going to pick x to be 0. Alright, the square root of 0 is actually 0. Okay, so my first point is right here. Okay, 0, 0. Alright, when I substitute x equal 1, the square root of 1 is 1. That's my next point right there. Alright, when I substitute x equal 2, okay, the square root of 2, okay, is approximately about 1.414. So not quite 1.5, but pretty close. So when I plug in x equal 2, right there, x is 2, I get an answer of 1.4, about 1.5, almost 1.5. Okay, I'll keep going. I'll say 3. All right, square root of 3 is about 1.732. Okay, all right, so when my x is 3, right there, my y value is about 1 3/4. All right, so I'm actually going to leave off the fractions this time. I'm going to not use 3.5 or 3 3/4 or any of those. Okay, so I'm going to pick, since I'm saying 4, I'm going to pick something bigger than 4. Okay, so I'm going to say 5. So let's see, y equals square root of x. So when I pick x as 5, a square root of 5 is about, well, let's see. And if I pick 6, square root of 6, I pick 7, square root of 7, I pick 8, square root of 8. If I were to pick 9, of course, I would get a 3. So these are somewhere between 2 and 3. So it's 2 point something, 2 point something. Yeah, I don't have a calculator in my hand right now. So, but whichever way I do. When I pick 5, I get something over 2, 6 over 2, 7 over 2, 8, somewhere between 2 and 3. So what's our limit? Okay, what's happening when I'm getting close to 4? Okay, the closest ones I have to, my closest answers to 4 are about here, and just right about here. Maybe it's about 2.2. So what would our guess be? What's the trend? Okay, we went from 0, y equals 0 to y equal 1 to y equal 1.414, 7.321, 1.732, and this one is probably about 2.2 something. So somewhere between 1.732 and 2.2. Our guess would probably, the trend would be, is 2. And the actual answer is 2. Limit as x approaches, the square root of x as x approaches 4 is 2. Alright? Okay, let's use this one. Square root of 2x. Or just plain 2x, not square root 2x. Okay, as x approaches 1. Alright, so let's see. Alright, so x and y equals 2x. So we can pick negative values. I'm going to pick a negative 1. 2 times a negative 1 is a negative 2. Okay. Let's see. 2 times a negative 1. Okay, y equals 2x plus 3. Okay, we substitute negative 1. 2 times a negative 1 is a negative 2 plus 3. Alright, we get a y value of positive 1. Okay, there's our first point right there. Okay, alright, we substitute our next value of 0. Okay, 2 times 0 is 0. 0 plus 3 is 3. Okay, so our next point will be right here. That's the y-intercept already. Alright, so I don't want to use 1. So I want to get close to 1. So I'm going to actually go back to my fraction, use 1/2. 2 times a half is 1 plus 3. I get an answer of 4. So when I use a positive a half, I get an answer of 4. Alright, let's try 3/4. Okay, 2 times 3/4 is 6/4. 6/4 is the same as 1 and 2/4, which is 1 and 1/2. 1 and 1/2 plus 3 is 4 and a half. So, closer I get to 1, the closer I get to the actual limit. Okay, and you can probably see the trend. We have a trend of getting to 1, then we have a 3, then a 4, then a 4 and a half. Okay, so let's go above 1. Okay, let's say 1 and 1/4. Let's do 1 and 1/2. Let's do 2, and let's do 3. Let's start at 3. Okay, 2 times, when I substitute 3 into x, 2 times 3 is 6, plus 3 is 9. Okay, so way up here past my 8. Okay, you can see it up here. So that's our point. Okay. Okay, at 2, let's see, 3 out of 9. When we substitute 2, put a 2 right there. 2 times 2 is 4, plus 3 is 7. So at x equals 2, our y value is 7. Okay. Alright, 1 and 1/2 is the same as 3 halves. Okay. 2 times 3 halves is a 3, plus 3 is 6. So our y value would be 6. So 1 and 1/2, we have a answer of 6. Okay. And 1 and 1/4 would be 5/4. Okay, 2 times 5/4 is 10/4. 4 goes into 10 2 times, the remainder of 2. So 10/4 is 2 and 2/4, 2 and a half. 2 and a half plus 3 is 5 and a half. So plug in, when we use 1 and 1/4, we just pass 1 down here, we get an answer of 5 and a half. Alright, so again, what's the trend? We're going from 1 to 3 to 4 to 4 and a half, and then we're going from 9 down to 7, down to 6, down to 5 and a half. So if I kept going, what would be the result? What were we anticipating? What we get in between those? We probably won't get a 5. Okay, and our answer indeed will be a 5. Okay. Alright, and you probably see how to get our answers. So why are we doing all this stuff, okay, when our answers seem really easy to find? Okay, let's do one more like this, a trig function. F of x equals sine of x. Alright, so when I do trig functions, I change my grid a little bit. Alright, here's my 0, my x-axis, but that 1.57 is really approximately pi over 2. And the 3.14, you know what that is, that's a pi. The 4.71 is about 3 pi over 2. And the 6.28, that's really representing our 2 pi. Okay. On the y scale, I count up by 0.5 and by 1 and down to. So this, and you see a typical sine graph. Pretty much one cycle, you see a little bit more of one cycle of a sine graph. Alright, so let's find the limit of sine of x as x approaches pi over 2. Here's pi over 2 right there. So we'll start. Okay, so my x, my sine of x is my output. So I'll pick 0. Sine of 0 is 0. Okay, that's right there. Okay, I'm going to pick pi over 4, which is exactly halfway between 0 and pi over 2, right where that blue x is, a little blue x right there. Okay. Alright, if you remember unit circle or use your calculator, the sine of pi over 4 is square root of 2 over 2. Now square root of 2 is approximately 1.432. When we divide that by 2, we get about 716, about that. Okay, so it's about 7.716, about that. So at 3 pi over 2, let's do that in red. That's halfway. 3 pi over 4 is halfway between pi over 4. This is pi over 4. And pi over 2, that's 3 pi over pi over 4. Whoops, I've gotten ahead of myself. I'm over to the next one. Pi over 4, excuse me, is about 7.716. So about 3/4 the way up. Okay, so get closer still to pi over 2. So let's do pi over 6's. Okay, let's see, pi over 2 is 3 pi over 6. Let's do 2 pi over 6. Okay, 2 pi over 6, and that's really the same as pi over 3. And if you remember unit circle, at that point the sign is square root of 3 over 2. Okay, the square root of 3 is about 1 point. This is 1.414. Alright, I get my square root of 2 and square root of 3 mixed up, 0.732. And when I divide that by 2, that's about 0.866, somewhere in there, but a little bit higher up. Okay, so pi over 3 is pretty close to pi over 2. It's not exactly halfway between pi over 4 and pi over 2. Okay, but it's actually a little bit closer to pi over 2 than pi over 4. But anyway, so, alright, put a gray dot there. Alright, so let's go above. Let's start here at, okay, pi over 3. We can do 2 pi over 3. It would be a little bit bigger than pi over 2. 3 pi over 4. And then we'll do pi. Let's start with pi. Down at the bottom, sine of pi is 0. Okay, so we can see that on the graph also. Right there, pi is 0. At 3 pi over 2, the sine is back to square root of 2 over 2. Which again, let me do it right this time, 1.414 divided by 2, which is about 0.707. 0.707. It's not a big difference. So 3 pi over 4 is actually halfway between pi over 2 and pi. And that would be right about here. And let's make that dot green. Match. Alright, one more. At 2 pi over 3, it's also sine. You know, that's the magic of sine graphs. They're symmetric about the y-axis, so you're going to get the same thing, about 8.866. Alright, and we'll make that one orange. Okay, so what's the trend? What are we anticipating? Okay, we're going from 0 to about 0.7 and 0.8. And then we do the other way, we have a 0, then to 0.7, then to 0.8. Each way they're getting larger. What do we guess it's going to be? We guess it's going to be 1. And that is the answer. Okay? So all this graphing stuff, when all we simply had to do is do what? Okay? Substitute. Okay? So, what's the limit of x squared as x approaches 2? Alright, well, we just plug in 2 here into this function. 2 squared is 4. Easy answer. Alright, no need to do all that graphing and figuring all that stuff. Okay, alright, what's the limit of the square root of x as x approaches 4? Yeah, we can plug 4 in there. You know, I just said not to. The square root of 4 is a 2. The answer is 2. Okay. All right. The next one we did earlier. Let's see. 2x plus 3. Okay. We plugged in 1. If we wanted to, we could avoid all that stuff. Substitute the 1 there. 2 times 1 plus 3. That's 2 plus 3. The limit is 5. Okay. And then, let's see, that last one we just got done doing. Alright, can we plug pi over 2 in? Yes. Okay. So, let's see, when we plug in pi over 2, the sine of pi over 2, that's a 1. Okay, answer is 1. Alright, so, one thing we see that limits are always y values. You plug in and you get an answer. But, sometimes we're not allowed to plug in. This is where that trend thing happens. For example, right here. Okay, limit of this function, x squared minus 4 over x minus 2. Okay, so we say we plug in 2 there, and we go plug in 2 there. Alright, here's our 2 right there. Alright, so our 2 squared is a 4. We get a 4 minus 4 on the top of our fraction. When we plug in 2 in the bottom, we get 2 minus 2. All of a sudden we have this thing, this indeterminate, it's called indeterminate form, 0 over 0. And we can't figure that out at all, what on earth that will be. Okay, we can't even say what that will be. Okay, so this is where that idea comes in, where we find values that are closer and closer to 2. Okay, and of course you can kind of do a graph and see what the answer would be, but let's do it this way. Okay, and this is a really good to see what that idea is probably anticipating. Okay, so here's our x, and our function is x squared minus 4 over x minus 2. Alright, I'm going to pick values for x. So I'll pick 0, I'll pick 1. We want to find the limit of this thing. So x squared minus 4 over x minus 2. Okay, 0, 1. Let's see, 1 and 1 half, 1 and 3/4. And let's do 2 and 1/4, 2 and a half, 3 and 4. Okay, so we plug in 0. Let's see, we get 0 squared minus 4, we get a negative 4. 0 minus 2 is a negative 2, you get an answer of 2. Let's plug in 1. 1 squared is 1, 1 minus 4 is a negative 3. 1 minus 2 is a negative 1, we get an answer of 3. Okay, so 0 we get an answer of 2. At 1 we get an answer of 3. Okay, 1 and 1 half. Okay, 1 and 1 half squared, 1 and 1 half is 3 halves. 3 halves squared is 9/4. Okay, 3 halves minus 2. It's a little rough. 9/4 minus 4 is 9/4. 4 is 16/4. 3 halves minus 4 halves. We're going to get a negative 7/4 over a negative 1 half, which is negative 7/4 over negative 2/4. The 4's cancel. Negative 7 over negative 2, we get 3 and a half. Okay, a lot of work for that point, but we got it. Okay, is there going to be an easy way? Yes, it's going to be an easy way. Alright, 1 3/4. Well, let's try it. 1 3/4. 1 3/4 is the same as 7/4. So 7/4 squared is 49 over 16. So the numerator I have 49 over 16 minus 4. I might as well go ahead and say that's 64 over 16. Okay. On the bottom I have, let's see, 7/4 minus 2. And that's the same as 8/4. Just speed us up a little bit. Let's see, 49 minus 64 is 15. So negative 15 over 16. And over negative 1/4. 7/4 minus 8/4. Okay, almost there. Negative 15 over 16 divided by Negative 4 over 16, we get negative 15 over negative 4, and that would be 3 3/4. Okay, so when I plug in 1 3/4 on the x-axis, I get 3 3/4. Okay, so we see a trend happening. We're going from 2 to 3. Our answer going from 2 to 3, from 3 to 3 1/2 to 3 3/4. All right, so to speed us up a little bit, when we plug in 2 1/4, we get 4 1/4, as you can imagine. 2 1/2, we're going to get 4 1/2. When we plug in 3, we're going to get 5. Okay, 3 squared is 9. 9 minus 4. 3 minus 2, we get 5 over 1, which is 5. Okay, and we plug in 4. 4 squared is 16 minus 4. 4 minus 2. 16 minus 4 is 12 over 2. We get a 6. Okay, what's the trend? We're going, from lower, going from 2 to 3, 3 to 3 1/2, 3 1/2 to 3 3/4, 6 to 5, 5 to 4 1/2, 4 1/2 to 4 1/4. So what is the trend? Somewhere, what would the exact be? Okay, and it looks like it's going to be 4. But again, we can't substitute in 2 and get our answer of 4. Okay, all right, I forgot to graph those. Let me graph those real quick. 4 is 6, and 3 we get a 5. At 2 1/2 we get 4 1/2, and at 2 1/4 we get that. Okay, so what are the orange graphs? What are the orange dots heading for? They're heading for that open dot. What are the green dots heading for? Okay, they're heading down for the open dot. Okay, and what y value is it? It's a 4. Okay, so limit is actually 4. Okay, how do we do that? We couldn't do that by direct substitution. Sometimes you get limits by direct substitution. Sometimes you can't. All right, that's pretty much, I want to stop there because there's some, so our answer is 4. Okay, so I'll give you a little tease on what's the next, because doing all this stuff is very laborious. We're not going to do that. There are definitely ways to do this. And you probably see that x squared minus 4, we can factor that. And then we have an x minus 2 on the bottom. So we see that if we factor that, the x minus 2 will cancel out. So what we would do is say the limit of this thing is really the same as the limit of this. Okay, and in this case we can plug in 2, and so we get our answer of 4. And so we'll do examples of that in another video. So all that is a long way around to saying what's a limit? It's a trend. Okay, what are you approaching? What are the answers getting close to when you get close to that that number you have there? From below, number smaller than that number, or numbers large.